All right, this time we have part 3 of chapter 15. I'm hoping that I can be able to squeeze the rest of the chapter into part 3. If not, there will be a part 4. So that's why the question mark. Okay, we're on page 297. And what happens if? I didn't mention previously. Different materials will expand at different rates when heated. Brass, for instance, expands at one rate, and iron expands at another. Now, I don't recall that to remind myself. Yes, when you heat them up, brass expands more, or faster, than iron expands. Interesting. Not only do they have different specific heat capacities, but they also have different rates of expansion. In fact, think about this for a second. That's why a thermometer works. What would happen if, in a thermometer, the glass expanded at exactly the same rate as the liquid inside? As the glass expands and the liquid expands, what would happen to the reading on the thermometer? Nothing. It wouldn't move up or down because everything is expanding together. Good thing that the liquid inside expands faster than the glass on the outside. That enables the water, or the alcohol or the mercury to be squeezed up that little tiny tube inside because it's expanding faster than the glass. But the glass does expand. There's, by the way, there's a problem with putting, say, glassware. If you take a jar, just ordinary glass jar at home, and put it on the stove with no water in it, and turn on the heat, there's a strong possibility that as the outside of the glass heats up, while the inside of the glass remains a little on the cooler side, because the outside is going to heat up rapidly, and it takes a little time for the inside to catch up with it. That makes the outside expand faster than the inside, and if the outside of the glass expands faster than the inside of the glass, something's going to give. It's going to crack. I have had the terrible experience of having a piece of bakeware, a glass pan, that we took out of the oven, placed it on the cool stovetop, and the moment that thing hit the cold stovetop, it cooled down the bottom surface of that container a lot faster than the inside. And because that cooled off rapidly and contracted, while the other side of the glass did not contract nearly as fast, the whole bottom of the pan just snapped, cracked, broke out. Had another bad experience. We're going to play with, on our last video, I will show you liquid nitrogen. That's my plan anyway. Liquid nitrogen is, I've forgotten what the temperature is. Liquid nitrogen is, I believe, 300 something degrees below 0 Fahrenheit. I had some liquid nitrogen in a glass bowl. I like to swish it around, it really does cool things. But one time I had a little bit too much in there, and that liquid nitrogen cooled down the inside of the bowl a whole lot faster than it was able to cool off the outside of the bowl. And that difference in the inside and outside temperatures caused that glass to shatter in my hand. And the whole thing just went to the floor. It was very scary and embarrassing since it was right in the middle of a class demonstration. But yeah, it can be very dangerous if you pour, in fact, you pour very, very hot liquid, like hot grease, right off the stove, pour it into a glass jar. As the inside of that jar heats up very quickly, the outside doesn't heat up as quickly, and that jar can just crumble, just snap, bang. It's kind of a loud crack sound, and it will fall apart. Not a good thing. I've heard that if you put a knife in the jar first and then pour the grease in, that knife will absorb enough of the energy that it keeps the glass from breaking. I don't know. I'm not going to try it. I'd rather just find some other way to let the grease cool down first before you put it in the jar, if you're going to put it in a jar. There's a, you've heard of Pyrex. This container is designed, this is a genuine Pyrex container, it says right here Pyrex. This is designed to have more even expansion. You can heat this thing up on a flame and it's not going to, both the inside and the outside are going to expand at about the same rate, which enables it to be heated up without cracking. Special kind of glass, brand name Pyrex. Paul Hewitt says that when a dentist puts a filling in your teeth, he uses a material that's designed to have the same rate of expansion as teeth. So if your teeth get really cold, maybe you're chewing ice or something, which is probably not a good idea, but if your teeth get really cold, your teeth and the filling both contract together. If they didn't contract together, that filling is going to break loose and come out. There's cookware called Pyrex. You go to Walmart, buy some glass pans that say Pyrex on them. There's bad news there. To save money, this is just, I can't believe they did this. To save money, I understand, the Pyrex company started making Pyrex cookware, not labware. Labware is good. But cookware is now made with a cheaper material that is not so, shall we say, heat proof. The pan that I had the bottom break right out of it, that was called Pyrex. Modern American-made Pyrex is awful. But if you go online, as we did later, you go online and find a Pyrex company in Europe and have them send it to you from Europe. That is the real thing. You can tell the difference because the cheap stuff in the United States is very clear, has very, very little color to it. But the good stuff that you get from Europe has a green tint to it. That green tint tells you, that's the good stuff. It's not nearly as likely to shatter on you. And you don't want your cookware shattering. So we bought a whole set of cookware from Europe, and it wasn't all that expensive. And we found that we've never had a problem with it. It has never broken on us. What happens if you have a strip of, say, brass that has a particular rate of expansion, and you fuse that together with a strip of iron that has a lower rate of expansion? And then you heat this thing up, put a flame to it. Okay, that's not a bad looking flame. There's my candle. Okay. Put a flame to this thing. As the metals heat up, if the brass expands faster than the iron, what's going to happen? This thing is going to bend. Or if you cool it down, it's going to go the other way. And I just happen to have, the reason I've got a flame going here, is because I happen to have a genuine, this is called a bimetallic strip, for obvious reasons. Bimetallic strip. It's bimetallic because it's made of two different metals. I don't know exactly what these metals are, but I'm going to assume probably some form of iron on one side and brass on the other. You really, well, if you look up close, you can see the difference. One side has more of a pretty golden look to it. The other side is clearly a silvery look. You can see the difference up close. But if I put this thing on, now which side is which? This is what I assume is the brass side. If that's the brass side, and if this is some form of iron on the other side, when I put it over the flame, I would expect the brass to expand faster. I would expect it to bend like this. Let's see if that's the right direction. If it goes the wrong direction, well, those aren't the materials. It's made of something else. But let's see as I heat this thing up. I trust you can see that. Well, let's get it where I know you can see it. We'll put it right here in front of my face. Oh, look at that. Look at that. I know it's kind of small, kind of thin. Maybe I need to get up closer here. And it is indeed bending in the predicted direction. And know that bending is not permanent. If I allow it to cool off, maybe if I do that a little bit to help it cool off. It will indeed go back where it was, ever so slowly, but as it cools off, it returns to its original position. Oh, I sure hope you can see that. I know it's kind of small, but maybe if I tilt it this way, you can see it better. I don't know. I hope you can see it well. I can make it go back the other way again, heat it up, and sure enough, it curls toward the flame. Mr. Peer, yes? What if you turn it over? Oh, okay. If I turn it over, it makes no difference. Now it will curl away from the flame because the side nearest the flame now expands faster because that's the material it's made of. Pretty neat. And then take the flame away and it will straighten out again. A bimetallic strip. What is it good for? Oh, I'm glad you asked. I need to find a place to put this where the heat won't cause damage. Oh, my metal file cabinet. And put that down for a moment. And grab, okay, where did I put my, there it is. One moment. This is a thermostat that came out of my house. When we got a new thermostat, I salvaged this one for physics purposes. If I take the thing apart, we have in here a really neat concept. Okay, I lost something. Oh, someplace between here and the science lab, something fell out of this that I really did not want to lose. And it's missing now. Bummer. Okay, well, we'll do without it. That's all right for now. We have here 2 tubes of mercury. Mercury is known for 3 things that are important to us right now. Thing number 1, it's a metallic liquid. Maybe that's 2 things. It's a metal, it conducts electricity very nicely, and it's a liquid at room temperature. It's pretty neat stuff. It's also known for being very heavy, 13 times heavier than water. Inside this, I don't know if you can see it very well, I'll let the camera focus on it perhaps. Inside here, we have these 2 little blobs of mercury. You see them going back and forth in there, I hope you do anyway. What's surprising about this, especially when you shake this, you know how you can feel something's inertia by shaking it? This thing, you can feel those little blobs of mercury going back and forth because they've got a lot of mass, a lot of inertia. And this thing feels heavier than it has any right to feel because of the mercury in those tubes. Imagine having tubes 13 times larger than these filled with water. Yeah, that's what this thing feels like. It's it's fun to feel that inertia, and it's pretty cool. But what's special about these? As the house temperature goes one way, as it say heats up, there's a bimetallic strip involved here. As this thing heats up, it's going to turn this way, and as it turns this way, the mercury in this tube comes down here and just minds its own business, while the mercury in this tube comes down here and touches 2 electrodes that turn on the air conditioning as the house heats up. Then when the house cools down, if it cools down too much, the mercury goes to the other side. Now this one is just doing nothing, minding its own business, while this one is now touching 2 electrodes here that turns on the heat. So what causes this thing to tilt one way or the other? Well, this big black thing, it didn't used to be black. It became black because I've touched it with a flame so many times. This thing here in the middle, this coil of wire, the coil of metal here, is actually a coiled bimetallic strip. If I heat this up, you'll see it begin to unwind. If I when it cools down, you'll see it go back the other way. Now, I've got to be very careful. I'm always nervous about this. If I heat up the wrong thing, if I get these glass tubes hot, I don't know if there's a vacuum in there or if there's gas in there. If there's gas in there, it could expand and crack the tube, or even just thermal expansion of the glass could crack the tube, and we would have a mercury spill, which is not a good thing. I'm making myself nervous. I really am. But hopefully we can see this as I try to heat up that, what you'll notice when I get up the courage to do this, as I heat this up, you'll see the glass tubes tilt, I believe, that direction. And then when I take the flame off, they'll start to go back again. Hopefully hopefully you can see this, and hopefully I will not have a major disaster. Oh, there it goes. Yep, see it turning? Cool. And then when I take the heat off, it will slowly but surely, I said it will, well, it takes a while to cool off. It heats up with this flame a lot faster than it cools down. But with time, it will come back to where it was. It's not a permanent change, really. I can get it to go farther by heating it up some more. There, you can see it moving. Rather obviously, right? Pretty neat. Look how far it is now. So it's a bimetallic strip. That's one of the great uses of bimetallic strips, used in household thermostats. Hey, as long as I've got a flame going here, have you ever seen this trick? Totally off topic. If I, by the way, the hot part of the flame is above the flame, not in the middle. I can do this and it doesn't hurt at all. I can even touch the wick. I'd rather not do that right now because I might make hot wax splatter around. But you can do that, doesn't hurt at all. But consider this now. This room is very still. The air conditioning and heating systems are not on. The flame's going straight up, which is very good for what I want to show you next. I wonder if I should get closer to you for this. Let me turn around here. I want to make sure that the candle is well in. Okay, that's good enough. You can't see the base, but you don't need to see the base for this. Although seeing the base would be good. Tell you what, let's do this. I'm going to lower the camera. If I undo that and crank this down, because I would like to have the flame against the dark background. Oh yeah, there we go. Oh, that's nice. Look at that. Cool. All right. I'm going to blow the candle out, and I'm going to attempt to light the smoke. The smoke contains unburned fuel. There will be a smoke trail coming up. I'm going to take a lit match and try to light the smoke trail, and the flame will go right down the smoke trail and relight the candle. No. Yes. Pretty cool, huh? That one wasn't nearly as good. Let's try it again. I've had it go as much as maybe 5 or 6 inches. Maybe back up against the black background. Oh, that was a nice one. That was a very, very short one there. So I got one. How long was that? It was about maybe 3 inches I got it to go just now. Pretty neat. We'd play with that more, but that's not the purpose of this chapter. Okay, so back to the book. Get rid of my matches here. Get rid of my flame. Hope I'll set off any smoke detectors. I did that once. Set off a smoke detector. That was not fun. Fire department came and everything. It was really embarrassing. Yes, hope to never do that again. Okay, that was years ago. There's a diagram of a simple thermostat on page 298 with a bimetallic strip in red. Now, water does something really awesomely cool and special. And this will be the last topic of the chapter. Water, like anything else, expands when heated. Oh, you're down so low. Do I need to readjust you? Yeah, let's bring you back up where you were. Oh, and I see that my screensaver timed out too. Okay, my crank here doesn't want to crank. There we go. Bring it back up where it belongs. Okay, that's pretty good. And let's get rid of my screensaver. One moment. Okay, we're good to go. Now, as I was saying, water expands when heated. Well, sort of. Sometimes water contracts when heated. Here's the deal. Suppose I have some water at, say, 10 degrees Celsius. Now remember, water freezes at what? Yeah, water freezes at 0. So I got water at 10 degrees Celsius. otherwise known as, I'm not going to try to guess what that is in Fahrenheit. It's whatever in Fahrenheit. Now, suppose I cool this water down. I put it in the freezer, and the water comes down to 9 degrees. As the water cools down, it will contract. I bring it down to 8 degrees. It contracts. I bring it down to 7 degrees. It contracts. I bring it down to 6 degrees. It contracts. I bring it down to 5 degrees. It contracts. I bring it down to 4 degrees. It contracts. I bring it down to 3 degrees. It expands. I take it down to 2 degrees. It expands more. I take it down to 1 degree. It expands more. I take it down to 0 degrees. It expands more. And as I remove more heat energy and more heat energy and more heat energy, finally that 0 degree water freezes. Once it freezes, then as I bring its temperature down even farther, it once again begins to contract as we would expect it to. So there's that mystical, magical range of temperatures from 4 degrees down to 0, from 4 degrees down to 0 degrees, where water does the opposite of what we would expect. Instead of contracting from 4 down to 0, it expands. It expands so much that it's never again going to be as dense as it was at 4 degrees. 4 degree water is as dense as it will ever get. This has some really awesome implications. The reason why that happens, by the way, when that water hits 4 degrees, it's starting to think about trying to freeze. And water molecules will start to link up with other water molecules into partial crystals, but then they get bebopped around by other molecules and get broken apart. But at 4 degrees, molecules are starting to try to link together and make crystals, and then they break apart and others get together. And the ones that are kind of coming together and temporarily, they're causing the water to require more space. They're causing it to expand. The closer you get to 0, the more of them are beginning to link up and they're taking up even more space. These water crystals take more space than liquid water as the molecules start to try to link up and form crystals. When it gets to 0 degrees, that's when everything begins to come together as one crystal and the water freezes. So between 4 and 0, as we go down in temperature, the water actually expands. So that means that 0 degree ice is as, what's the opposite of dense? As light as water is ever going to get. And 4 degree water is as dense as water is ever going to get. Once this frozen water begins to contract, it will never contract down to what it was when it was at 4 degrees. 4 degree water is as dense as water can get. So what does all that imply then? I'm going to flip over to page 301. Let's consider a pond. We've got ground here, we've got water in a pond. Oh, it's not blue water this time, it's yellow water. That's really gross. Okay, that's all right. Now suppose that this pond starts off, I've got a little note here someplace that helps me not get mixed up in my illustration. Oh no, have I lost my note? I'm just all kinds of things. I lost my little bimetallic strip thermometer, and I lost my, oh, there's my note, okay. Yeah, so I don't get messed up here. Let's suppose that the water right now is at 10 degrees Celsius. And let's suppose we have air at, just we'll pick a random low number, maybe it's negative 10 degrees Celsius. Very cold air, and a relatively warm pond. Well, this cold air is going to cause the warmer water here to give up its heat. Remember, heat energy is going to be transferred from an area of high temperature to an area of low temperature. So this warmer water is going to give up its energy to the cold air. It's not like, the cold air is not making the water warm. It's more like the warm water is making the air warmer, as the pond water gives up its heat to the cold air. The flow is always from high temperature to low temperature. So as the pond gives up its heat here at the surface where it's in contact with the cold air, the surface temperature might go down to 9 degrees. But just below that there might be some 10-degree water here. What happens then? The 9-degree water has shrunk a little bit. As you cool it down, it contracts. That makes this water a little bit heavier, so it's going to sink to the bottom, while the 10-degree water comes up to the top. Well, that flow is going to continue as this 10-degree water cools down to 9 and sinks, and if there's any other 10-degree water here, it's going to cool down, turn to 9 and sink, and at some point everything's going to be 9 degrees, but then this 9-degree water up here is going to go to 8 degrees because it's still in contact with the cold air, but it's surrounded by 9-degree water, so it's going to sink while the 9 comes up. And that cycle continues as the colder water sinks and the warmer water rises until something special happens. It'll continue that cycle, that flow of colder, because of the air, colder water sinking, warmer water rising. That flow continues until it hits 4 degrees. Once everything is at 4 degrees, it stops moving. And then something really neat happens. You say, well, what happens when this hits 3 degrees? Okay, at 3 degrees, from 4 down to 3, the water no longer contracts, remember. From 4 to 3, the water actually expands. That means that this water is now less dense than that water. So this water is going to stay right where it is because it's now the least dense of all the water. It stays at the top. Well, this water is happy to stay down there. The water at the bottom just stays at 4 degrees. While the surface water keeps going down and down and down. And finally, that surface water is able to freeze. And you get a layer of ice on top. While the water down here is still at 4 degrees, and the fish apparently are quite happy to live in that. That's why a frozen pond doesn't kill the fish, because the fish are down here in the 4-degree water, just having a good old time, loving life. While the ice, being the least dense, is sitting on the top. Now, ice is also a very good insulator. What's that mean? Ice does not conduct heat very well. So now that you have a layer of ice, the heat is having a harder time getting through to the air. It slows down. So have you ever noticed how you'll get a thin layer of ice on a pond very quickly? But for that ice to get thick enough to be safe to skate on, takes a long time. Yeah, you can get a thin layer of ice very fast, but a thick layer takes longer because the thicker that ice gets, the more it insulates the water below, the less able the water is to give up its heat to the air, and so it grows very slowly. And the ice gets thicker and thicker and thicker, but it always stays on top because it's the least dense of all the waters, and the more dense 4-degree water stays at the bottom. So you go to, in the middle of the winter, you find a lake someplace. That lake may be frozen on top, but one thing you can be sure of, at the bottom of that lake, the water temperature is going to be 4 degrees. Guaranteed. Guaranteed. Now, there are some places where the weather is cold enough that even at the bottom of the pond or lake, it can still be really cold water down there. But generally speaking, large enough pond or a lake, the water at the bottom is going to be 4 degrees. Pretty much year-round, I believe. Yeah, doesn't matter what time of year, the bottom is always going to be 4 degrees. Think what would happen if this did not happen. God has done a rather wondrous thing here. If water did not have that property of expanding from 4 down to 0, if it continued to contract, then where would that cold water go? It would go straight to the bottom. Where would it freeze? It would freeze at the bottom because water is no longer expanding. When it freezes, it's contracting. So that cold water and that ice would accumulate at the bottom. and more would accumulate, and more would accumulate, and more would accumulate. As the water here keeps getting colder and sinks to the bottom, it gets colder and sinks to the bottom, it gets colder and sinks to the bottom. Pretty soon, this lake is going to be like one solid block of ice, and it's going to take forever for that lake to thaw out, and all the fish are going to be frozen solid. Dead. Frozen in a solid block of ice that takes like forever to thaw out. So life on Earth would not be possible if water did not expand from 4 degrees down to 0. And it's only from 4 down to 0. At all of the temperatures, it expands when heated. Did I say that right? Yes. Yes. Now, what else do we need to mention here? Oh, yes. One time back at my old school, back at Montrose Christian, I looked in the freezer and I saw this water bottle. It was not mine. I don't know who it belonged to. It was in the freezer, full of water, and I reached in there, saw this thing, and I said, I want that. So I took it. I didn't ask. I don't know who it belonged to. I saw it, I wanted it, I took it. Why would I do that? Well, because, as I said, it was full of water. And it was in the freezer. What happens when water gets frozen, when water freezes? Well, from 4 degrees Celsius down to 0, it's expanding. That expansion, you can't hold that back. It's going to happen. It does expand. So what happened, I looked in the freezer and I saw this thing and I noticed that. This is a metal water container. That's pretty heavy duty stuff. But that expanding water caused it to crack right down the side like that. And the frozen ice was had oozed out that crack. And the reason I grabbed it is because I knew the owner didn't want it anymore, but I sure did, because that's a really cool example. That's why we have problems in the winter with roads. Water gets into the cracks in the roads, and then if the road gets cold enough, that water in the crack expands. As that water expands, it breaks the pavement, and you end up with, potholes. Then along comes a snowplow and hits that loose material and breaks it up even more, and you get a pothole that grows bigger and bigger and bigger. But it's all caused by water going into cracks and expanding. We have some small cracks in our sidewalk in front of our house, and years ago I got some material at Home Depot, some caulk, and I filled all those cracks. Because if you don't fill your cracks, water goes in there, in the winter, it expands, it breaks your sidewalk to pieces. So you want to keep your sidewalk cracks filled with caulk. Buy special caulk. You can get caulk that matches the color of the sidewalk and especially designed for concrete. But you want to fill those cracks. Was there some other example I was thinking of regarding that? Maybe not. I feel like there was some other good example. But, maybe not. Okay, I heard when I was a kid, they used to deliver milk to our house. And they would they were in glass bottles, and they would put it in the special insulated container on the porch. And every day you would go out there and you would open up this box and pull out the milk bottles. That was back in the probably 50s, now that'd be in the 60s, sometime in the 60s when I would remember that. And they had these kind of foil caps on the bottles. If that thing sat in the winter on the porch in that box for too long, the milk would freeze. Well, fortunately, the milk was able to freeze and expand, and it came up the neck of the bottle, and it would pop that cap off, and you would end up with this thing. You'd have a bottle kind of like this. I bet some of your parents might remember this. And you would have this thing of frozen milk kind of sitting out here, kind of looking interesting, coming out there with the cap maybe laying on top here, just kind of chilling. It wasn't uncommon. You just had to remember to get your milk out of the box before it froze. Okay, any other examples I can think of regarding the expansion of water or the expansion of anything when it heats up, or the contraction when it cools down? No, I think I'm out of ideas. As always, folks, if you don't read the material in the book, you will be missing important details. I do not ever guarantee that I cover everything that could be on the test. Read the book. It's easy reading, as you know. For those of you who have never bothered reading the book, you may not realize how easy the reading is. The chapters are fairly short. This chapter is, wow, it goes from page page 290 to page 301. This chapter is only 11 pages, okay? You can do this. Read the book before you take the test. The assignment. Tell you what, instead of describing the assignment right now, I will put the assignment in the Google Classroom post, or for you Ch15 students, I'll put it in the email. So I don't have to think of what the assignment is right at this moment. I will break the assignment into two parts for the Covenant Life students, and both parts will be together as one for the Ch15 students, okay, as usual. And that's it. So, see you later. We are done with chapter 15.